All right, so the way this works is every Friday I'm gonna do a quick 1 hour recitation. And sometimes this will be kind of me looking at the topics that Zach goes over in a slightly different light. Sometimes it's just me doing summaries of what he's done. And other times it's me going through stuff that is directly useful for the quizzes or the homeworks. So when there's like a new homework out, I will like spend some time here going through the homework. But the idea is that this is supposed to be an hour just for me to kind of go through stuff that maybe Zach didn't quite go through in the way that I think would be best for people who haven't seen it before. And it's a really good time for people to ask questions that they're maybe like afraid to ask Zach in class. I'd be more than happy to answer anything. So let's get started. Today is the 19th. All right, so today we have a few super basic topics that are very simple if you haven't seen them before, but knowing them is going to be crucial for understanding the rest of the class. So the first thing is going to be linear systems. I know CMU has a linear systems class in ECE, but it's not taken by that many people in RI. So we kind of assume that maybe you haven't seen a lot of this before. Then we're gonna do some derivative formalisms. People really define the same things differently, you'll see. And that is a little painful to deal with. So we're going to give you kind of one direct way of this is how we deal with derivatives in this class. And you'll just use that for everything and you'll be okay. The next thing is Taylor series, which I know we all learned in high school and like in theory know. And the way we're going to be using it now is going to be in like a multivariate sense, which can really throw some people for a loop. So we're just going to go through kind of first and second order Taylor series, what these look like for specific functions, how they deal with functions with multiple inputs. And this is what shows up in our control problems. And again, these things seem very simple, but understanding them is just going to take you no time at all. And once you really get them, it makes the rest of the class just kind of fall into place. So this is like super critical. All right, so the first thing, Zach has gone over this in class. The idea of like a dynamic system. And so when we talk about dynamic systems, we talk about one of two types. Either it's continuous or it's discretized. And so what you'll see in, for all the mechies, this is kind of what you do in undergrad in your dynamics class or your ODE class, is you think about these ordinary differential equations, which just means that I have a derivative of x with respect to time. This is where the dot comes from, is a function of x and u. And it can be a function of many different variables. I will choose x and u because in this class, we think about dynamic systems that are a function of the state of the system x and the control u. This is state. This is control. And as just a quick reminder, Zach went over this in class, but the idea of a state, for those of you that haven't seen it before, it's everything I need to fully reconstruct my system as it is. And the idea is that with that state, I can fully describe everything. I don't need more or less to do so. So what's very common in mechanical systems or control problems is what we'll see is that this state will actually be divided into two things. This state will be a configuration Q and a velocity V. So, example of this is if I have like a satellite or something, my configuration, this is where my position, so R, like my three-dimensional vector in Cartesian space, and then my velocity is my V velocity. It's also in Cartesian space. So the idea is that any dynamic system is going to have a configuration and a velocity. If this was a robot arm that had like, 7 links or something, they're all like one degree of freedom links, what we'd have is that we'd say that this configuration is all the joint angles, and this velocity is all the joint velocities. So when we see these, put these together, this will be the state. But sometimes, you'll see other classes talk about one or the other in more detail. And when Zach wrote out like the manipulator equation, this is using this assumption that we can break this state down into a configuration and a velocity. All right, the next thing we're going to talk about is once we discretize this. So let's just assume that magically I can solve this ODE and I get what's a difference equation. And this is like really worth like taking a sec to think about. So most continuous time ODEs, we cannot.
Hello, recitation.
Sorry. Most of these continuous time ODEs we cannot solve. So even very simple systems, like if I take a pendulum, if I take a double pendulum, it's a very simple ODE. It's been studied for hundreds of years. There's still no solution to it. And this is important for us because I feel like when you take an ODE class in undergrad, the idea is to write down these ODEs, then use clever techniques to solve them. And once we solve them, then we can do all sorts of cool analysis on them. And in the kind of in the real world, or at least in the robotic control sense, there are no solutions to these ODEs. So what we have to do is we have to use some form of numerical integration, something numerically to approximate the solution to these. And so if you ever see like Euler's method or like a Runge-Kutta method, these are solving ODEs. So most importantly for this class, we do not assume we can solve x dot equals, and that's okay. So we can't solve this exactly in closed form. That's totally fine. Then I'll drop a very big asterisk right here because I'm about to show one special case where we can do this. And the idea with a discretized dynamical system is that I have a state x at time step k, I have a control u at time step k, and I have some function that says, all right, given this state and this action, I put it into a function, it tells me what the state at the next action is going to be. So for those of you that have seen like the grid world example where like I'm moving along the grid, your state would be where you are in the grid, your action would be like up, down, left, or right, and then your next state would be the next grid you end up in, or the next square you end up in. So this broader idea of representing these systems that have a state and control and how they change over time, and we can talk about them in terms of the derivative for the ODE, for the continuous time, or we can talk about them in terms of the discrete sense. And what we'll find is that most of the time in this class, we really discretize everything. And the reason being is that there's a lot of classical optimal control stuff that focuses very heavily on this. And ultimately, when we put things into a computer, things get discretized anyway. And it kind of turns out that the earlier that we discretize, the easier our life becomes. So, classic optimal control really focuses on this. More modern optimal control that's kind of like, convex optimization based, or I guess numerical optimization based, really prefers using this. And we'll use both in this class, but with a little more of an emphasis on the discretized version. All right, so now let's talk about the asterisks that I drew right here, which is, we cannot solve these. Well, we can solve some of them, a very specific subset of them. So now let's talk about linear ODEs. So linear ODE, and I'm just going to ditch the control for a little bit. So linear ODEs is just saying x dot equals a of x. The idea is that x is going to be some vector. This means x is like an n-dimensional vector. And so when I write down x dot equals ax, what I'm really saying is that if I take the state x and I transform it with some matrix A, this gives me the continuous time derivative of this with respect to time. And it's important to note that we can always put things in this form if it's linear. So for instance, if I'll do a nice little example here. I'll actually modify this to be first order. First order ODE. And I'll make it a little more broad. So the idea of the first order ODE is that every single differential equation, every single ODE, sorry, can be represented as a first order differential equation. And this is super important because in your ODE class in undergrad, you'll be using all sorts of methods to solve second order ODEs and everything. And we can turn all of these ODEs into first order ODEs and then use all the same tooling. And this just really simplifies the way that you deal with these differential equations. It makes everything much easier down the road. So I'll give you an example of this. So if my state, say I have some configuration Q, the second derivative equals force over mass. So say I'm doing like an F equals ma sort of thing. I have written my differential equation that fully defines my system, and I've written it at the acceleration level. And this just means that the second derivative of what I care about is what's being represented right here. And this is not a first order ODE. This is a second order ODE, two dots right here. This is second order. I'm talking about the second derivative. What I can very easily do is I can transform any of these things into an arbitrary first order ODE. And I can do that with the following. So I can just say, here's some variable z. I'll make Z, actually I won't use Q here, um I'll use B just to make it more obvious. So I have some new state Z, right? And so right now I'm just kind of spitballing. I have a new state Z, and I'm going to make this B and B dot. So what I've done is I've taken this term B, of which I've described its second derivative, and I just put it into a new system where I just do B and B dot. And now if I try and write down the ODE for B, let's just write everything I already know. So this is B dot, B double dot, and this is equal to B dot, unsurprisingly. And then B double dot is F over M. So if I write this out in state space form, what I see is that I get, Z dot equals, actually I'll do it as the full term, B dot, B dot dot equals 1, 0, 0, 0. And all of a sudden, I have a first order ODE. And this can be done for an arbitrary number of orders for your ODE. So if I had a 10th order ODE, I would just stack up 9 of these things in the state. And I'll just write this kind of cascading thing. So you can work this out on your own and like make sure it actually makes sense. I'll do I'll do like a third, I guess like a third version of this. So just to make it super clear what we're doing. We won't deal with anything more than second order in this class, but just to show you that I can take any ODE and transform it into a first order ODE is really important as far as intuition goes. So if I had, B equals A, B dot plus C, B double dot plus D of B plus F. If this was my ODE for whatever reason, I could write down my whole thing as a first order ODE with the following. I could do B dot 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 then my state is B dot B dot dot. And this is B dot equals 0, 1, B double dot equals 0, 0, 1. And then for our B triple dot, we have A, C, D, F. So this is not an example that we'll ever encounter in a control problem. I'm just demonstrating how we can take a differential equation that is higher order than 1 and convert it into a first order differential equation. Does that make sense to everybody? I'll just circle this and say any order ODE first order ODE. That is the main takeaway from this. All right, so next thing we'll do is it linear? Is this a linear ODE? So on the quiz, you'll have a question that basically asks you, it gives you a bunch of ODEs and says, is this linear? So there's like, what you learned in linear algebra, there's like this classic idea of a function is linear if it satisfies these 3 properties. And like what you'll commonly see is, I'll just write down for a second and then I'll erase it because it's not important, but just in case you've seen it before, we're used to saying, okay, is this function linear? It is if, A plus B equals f of A plus f of B, and then, f of TA equals T f of A. So you've seen these things before where like the function is linear if it satisfies all these things. We are not going to worry about any of that in this class. Here's a very simple method to determine if your first order ODE is linear, if it can be put in this form. So if I have an arbitrary x dot equals f of xu, this function is linear if I can write it as such. X dot equals some matrix A times X, some matrix B times U. And these matrices, they don't have to be constant, but they can't be functions of X and U. So what you'll see very commonly is a linearly time varying system. And all this means is that these B's and A's, they change a little bit over time. So this will be a function of t. So here's an example of a ODE, and I'll make it x1 dot, x2 dot equals, and then here's my A matrix, x1, x2, and then my B matrix. And let's say I have two control inputs. This will be a 2 by 2, U1, U2. So being a linear ODE, this just means that every single item in these matrices is not a function of X and U. So as soon as I do, x2, nonlinear. If I put U1 right here, nonlinear. As soon as anything other than time varying constants show up in these 2 points right here, this whole ODE becomes nonlinear. So what you need is that you need everything here. So for these things, no X's or U's in there to be linear. Now things can be time varying. So like I could have, e to the t, sine t, cosine t, t squared, t factorial. Like you could literally put whatever you wanted to here. So tons of nonlinear stuff in t, but this function is linear in x and u. If I can write it out in this form such that it's the A and B matrices here and here contain no x's, no u's. And what you'll see is that for a lot of systems, you can do this and it's just fine. So for the double integrator system, Zach will talk about this over and over again, and you'll see him put it into this form. And he can, because when you separate out the ODE into these variables, you don't need anything other than constants in these matrices. If it's time varying, you can add the time varying constants, and it's still linear in X and U. And the way we talk about linearity is that it's always linear in certain variables. And so you'll see is that Zach will say it's linear. And what he means is, actually, I'll do a little like Zach translation right here. So when talking about a function of a state and control, Zach says it's linear. And really what he means is it's linear in X and U. So he says it's linear. What he means very specifically is that this function, f of x and u, it is linear in x and u. What that means is that I can construct the output of this function with a linear combination of the variables in x and u. And this is what this whole magic here corresponds to. I must be able to pull out these two matrices, normally go by A and B. I must be able to pull out these matrices, and there shouldn't be any x's or u's in there. And again, if you can't do this, then the function's nonlinear. And it will be very obvious throughout the class which these functions are linear and nonlinear. So for the quiz, I'll give you like 5 examples, 2 of which will be linear. And in there, that'll be, some obvious things that have a whole bunches of x's and u's in these matrices, nonlinear. Has a t, totally fine, because we're not talking about t. We're saying linear in x and u, not linear in time. So this idea of a function being linear in something is really critical and often gets omitted when people talk about this. So if you read a textbook, if you read, a paper, if you listen to Zach, this is almost never mentioned. But for those of you that haven't really had to think a lot about linear versus nonlinear, it's really important to know that when we talk about linear, we're always talking about in respect to certain variables. All right, so now this brings us to our favorite system, which is the linear dynamical system. So we'll do linear dynamical system. And this is kind of like, we love dealing with this, and I'll go into this in a little more depth, but basically x dot equals a of x. This is, and you can think about it, an autonomous linear system. So I give it an x, an initial condition, and I say run. And so what does this actually look like? So if x is a 2-dimensional variable, these are actually vector fields that we can visualize in a pretty nice way. So here's one, and then here's another. So think about this. What this is saying is that x dot equals a of x. The derivative, so in this case, the vector that we're looking at, this direction this thing is pointing is a function of where it is. So for instance, if I'm talking about right here, we can figure out what the x and y are. Or in this case, it's x1, x1, x2, x1, x2. So we figure out where this thing is, and this tells us the direction that this vector is pointing. And what we can do is the way we simulate these things is I can say, here is our initial condition. We start right here, and then we just let the vector field take it. And this is what it means this is what the solution to an ODE means, is it's going to follow some path along this thing that makes sense. And I can start somewhere else, get a different path, start here, get a different path, start here, get a different path. So it's dependent on where you initialize this. So the initial condition is a must-have in terms of simulating these ODEs. I must know where I'm starting. In this case, it's called a phase plane. It's just a fancy way of saying this is a vector field for our two-dimensional ODE. And what the ODE is telling us is the direction this vector points as a function of x and u. And by being a linear ODE, it just means that it's a linear function of this. So nothing super special. But this is, I think, a good way to think about what these ODEs actually represent and combine it with something that you maybe have seen in a previous class or something. And just a little more specific. So now let's think about things in terms of how they evolve over time. So this is, wow, those are not straight. Here they are straight. So here is time. Here's our value x, it's a function of t. So I initialize this thing. I initialize this thing at some value right here, and it's defined by x dot equals f of x. So I don't assume linear, nonlinear, anything. And what this is saying is that I have some function here, and what the ODE is describing, this is the true function. What the differential equation is telling us is what is the slope at each of these time steps. And our ODE is telling us as a function of t what that slope is. So now let's go back to thinking about linear things for a second. And the reason that linear is so important in this class is because really the only things that we can solve are linear things. And this is true with like almost everything. So if it's like an arbitrary set of equations, if it's linear, I can solve it if it's solvable. If it's nonlinear, sometimes I can, sometimes I can't. And the same is true with ODEs. If it's a linear ODE, I can absolutely solve it. So if I have x dot equals a of x, I can solve this thing in closed form using the matrix exponential. So I can say x of t equals e to at times x of 0. And this is me saying if I want to figure out what x is after time t has passed, so actually a more generic way to put this is actually the following. So I'll do x of t plus delta t equals a of delta t. So given the value of x at time t, and giving the ODE, which is the A, this is the information we care about from the ODE. Given these two things, I can use the matrix exponential. I can use the matrix exponential to solve this thing in closed form for what it is. Just nothing in the chat. Okay. And so what we do is if you give me a linear ODE, I can solve it. Most ODEs, unsolvable. Linear ODEs, I can always solve. And I solve it with the matrix exponential. So I take the A, I exponentiate it times dt. This gives me another matrix that is the same size of A. So you can read up what the matrix exponential is. It's just like a big power series. There's very clever ways in modern linear algebra frameworks to compute these. And you can do them super fast depending on the size of it. And they don't actually do the full definition. It's a bunch of like numerical magic that happens as far as computing these things. All this to say, we can compute it very accurately, very quickly, and we just have to compute it once. So if you give me an ODE that's the form of x dot equals ax, I compute one matrix exponential, and I now know how to like broadcast this thing forward in time, like how to propagate it dt. So why is this useful for us? So it's useful for two ways. One, I can now solve the ODE. So because I can solve it, I can predict, given what the ODE is and how I initialized it, I can tell you what the value is at any point in time. So that's one nice thing about it. Second thing is that it gives me a way to think about the stability of it. So if I know the solution at every single point in time, I know if this thing is going to blow up or going to go to zero or what it's going to do. Because I have the closed form solution to it now, I can predict with 100% accuracy what this thing is going to do. And this is really helpful for stability. And as controls people, we care a lot about stability. And the third reason is that earlier we talked about continuous time ODEs versus a difference equation. This is our way of converting linear dynamical systems that are an ODE into a discrete time equation. So if you think about this, the way I wrote this right here is I have dt was the amount of time I wanted to propagate forward. So graphically, what this corresponds to is if I have some t plus dt, this is, this is our value of x. Given the information right here and how far this step size was, I was able to solve for what this value is. And dt can be anything. I don't have to assume dt is small or big. dt could be 10 years. It could be like a millisecond. So either way, this is closed form. It is exact, and it will give me the answer. And this is nice because if you give me an x dot equals ax, I can discretize it with this matrix exponential for a dt that I care about between time steps. And now I have a discrete time equation. So here's what this looks like. Here's a little timeline. This is, t of k plus 1, t of k plus 2. And between these things, if I have dt, and this is very common in robotics. So in robotics, say I'm worried about like a differential drive robot or something, I may simulate it at 10 hertz, which means that this dt is 1 over the frequency. So it's going to be a step every 0.1 seconds. And I want an equation that tells me, given my state in action, what happens 0.1 seconds from now. This is the time step that I care about. So when Zach says time step, he's talking about this dt. And what I've done is I've basically said that I now have a new equation, which is xk plus 1 equals e of a dt times x of k. And remember, this is not a function of the value of x. This is a function of the dt. So once I choose a time step, say I want it to be 0.1 seconds, 0.01 seconds, 0.5 seconds, it could be whatever. Once I choose that time step, it's always going to be 100% accurate. I choose whatever time step I want to. I compute one matrix exponential, and now I have a way to propagate the system forward for however long I want to. And we call this temporarily AD. This is our like discrete time A. And the reason I say temporarily is because, what you probably should do is that every time you're writing a continuous time ODE, you should use x dot equals ax. And every time you're writing a discrete time difference equation, it should be xk plus 1 equals AD times xk. And what you'll see is that Zach is soon going to omit all these things, all these D's that you see. And now whenever you see A, he's talking about the discrete time A. So he'll make this clear in class. You'll see this over and over again, but this is kind of the main idea. So what I've done here is I've taken a continuous time ODE that's x dot equals ax. I take the matrix exponential. Now I have the discrete time equation. So now we can do the same thing with controls, right? Because this is a controls class. We care about influencing these ODEs. I don't just need to predict it throughout time. I want to know what happens when I actually start controlling it. And so to do that, first, let's talk about the way in which we want to control these things and the way robots actually control things.
I have a question.
Mm-hmm.
So if we are taking this matrix exponential and we are getting a discrete system, then where does the Range Katta and the forward Euler and all those methods come in? Where do they come in?
Okay, this is a great question. So let me make this clear. So we have linear, nonlinear. So these are, they joke that there's two types of differential equations, good ones and bad ones, and there's no good ones. There's linear and nonlinear ones, and I'd argue that the linear ones are the good ones. So this means x dot equals a of x. Nonlinear is cannot be represented that way, f of x. So solve with EAT. I can solve this differential equation exactly with the matrix exponential. For nonlinear things, all bets are off. There's probably not a closed form solution. Even for very simple systems, like I said, a pendulum, there is no closed form solution. So what do? We numerically solve it. And this is where we see Euler, RK4, midpoint. If you're using MATLAB, you use ODE 45 before. This is what's going on. So this is a little more complicated, but it's an ODE solver that is numerical, and it's a mix of two Runge-Kutta methods. So if it's linear, I can solve it in closed form with a matrix exponential. If it's nonlinear, all bets are off. I probably can't solve it in closed form, but I can for sure solve it numerically. And the numerical methods for solving these ODEs, this is Euler's method, RK4, midpoint. And so let me just do a kind of a quick example. So I won't go through RK4 and midpoint yet. Zach will go through these. I'll go through Euler really quickly. And what I'll say is that if I have some function x dot equals f of x, this is my ODE, and this is nonlinear, I don't know the solution. The easiest and probably dumbest way that I could solve this is I could just use Euler's method, which says that x k plus 1 equals x of k plus x dot k times dt. And what this is doing graphically is I have some value right here. I take the slope, of this, and I just go ahead and broadcast it forward. One time step. And then, I go here, I compute a new slope. New slope tells me right here. Just go ahead and broadcast this thing forward. So the idea of using Euler's method to numerically solve ODEs is just I take information about the state and the current derivative, and I approximate what it is the next step. And so Euler's method is very bad in terms of the stability. It'll basically introduce artificial instability into these equations. So Euler's method, even though it's super common, is like really not the right thing to use basically ever. There's like exceedingly rare is it that Euler's method is the proper thing to use. What's way more common is to use midpoint or RK4, and this is what we'll use all throughout the class. And these do a bunch of midpoint's a little simpler, but RK4 does a bunch of clever stuff to compute what that next value is based on the derivative at a few different points on that time step. So all this to say, linear ODEs, I solve with the matrix exponential. Nonlinear ODEs, I have to resort to numerical methods like Euler, RK4, midpoint. This is where I'm numerically solving the ODE opposed to solving it in closed form.
Okay, so these methods will directly discretize the nonlinear system, nonlinear ODEs and solve them. But if I linearize the system using the Taylor expansion, then I can solve it using the matrix exponential.
So that is an exponential integrator, which is probably not something you would want to use for most cases. There's one very rare case where it does make sense to do that, but what we'll see as we go through our linearization thing in a little bit, that we really don't want to do that. So I'd much rather, it's much more inexpensive and much more accurate to solve a nonlinear ODE using RK4 and midpoint than it is to take a full Taylor series, assume it's linear, and then broadcast it forward. And numerically, there's a few reasons, but I think conceptually, one reason is that when I take my Taylor series, actually, yeah, this is a good thing to maybe talk about. So if I have, TK, TK plus 1, the way something like RK4 works is RK4 is going to compute derivative information at 4 different places. And it's going to use a combination of these derivatives that we calculate at different places to figure out what it is at this final time step. So what it is right here. The method you just described, where I take the information at the current time step and I take a bunch of derivatives and I form a Taylor series. So say you want to form a first order Taylor series. I linearize this thing and then solve it.
Hmm.
This is again Euler's method. So
Okay.
if I approximate I'll go through Taylor series in a sec, so I won't kind of like try and cut into that right now. But basically, if I take this system and I approximate it as linear and then try and solve it by projecting it forward, this is exactly what Euler's method is doing. And it's not a good thing to do, generally. Does that make sense?
Right. Okay. So if you have a non-linear system, we should not linearize it. We should just directly solve it using Runge-Kutta.
In terms of solving the ODEs, yes.
Okay.
Yes. We will do all sorts of linearization, but we will never linearize to solve the ODE. We will linearize to do a bunch of other things, but we linearize after it's been discretized, and that's mostly for the control, I guess like the controllability, the ease of controllability. We don't use it to actually solve the ODEs. For solving the ODEs, if we can't solve it because it's not linear, we always use RK4, basically almost always RK4.
Okay.
All right, so the next thing is the stability. So Zach mentioned this in class. I'm just going to write them again because this is a quiz question. If it's a continuous time system of x dot equals a of x, what I can say is that if the real parts of the eigenvalues of a are less than 0, I'm stable. Shall do. I'll write this out like it's code. If all the real eigenvalues are less than 0, it's stable. This is saying that I can take my linear ODE, I can look at this A matrix, I can take an eigen decomposition to give me what the eigenvalues are. And from those values, if the real parts of all of them are less than 0, then it's stable. And Zach will go over this in class in more detail, but it basically comes down to when I use the matrix exponential to solve this thing, if I think about it in the 1D case, I either have a decaying exponential or a blowing up exponential. So I'll do a very simple case. If it's a 1D thing, x equals ax, so a is just a scalar. So x is just a scalar. The solution to this thing is not going to be x k plus 1 equals e a dt times x. So what does this mean? This means that if a is positive, then e to the a is positive, and so what I get is, or e to the a is greater than 1. So what I get is this thing is just going to keep blowing up. Now, if a is negative, this thing will decay nicely. And then, if there's imaginary numbers there, you'll get a bunch of like, oscillating behavior. If it's purely imaginary with no real, it'll just be a perfect sine wave. So all this to say that I'm looking at the values of A in our linear ODE, and I look at the eigenvalues, and I want the real components of those to be less than 0. That means we're stable. And for the discrete time case, we have a similarly as simple xk plus 1 equals a of d xk. And what I'm saying is that should I talk about this yet? Yeah, also I'll do the norm. So all norm eigs a less than 1. So before with continuous time, I want the real part of all the eigenvalues to be less than 0. Now in the discrete time case, I want the norm of all these eigenvalues So if the eigenvalue is imaginary, the norm of an imaginary number, this is the same as like the modulus or the magnitude of it. The norm of this thing must be less than 1. So I want it to be shrinking. And you'll see these, and we'll go over these a little bit in the homework, but the main idea is that continuous time, real less than 0, discrete time, norm less than 1. So this is on the quiz, and these are just the two stability conditions. All right. Next thing we're going to talk about is control, right? Because ultimately we care about how we control these things. And so we want some input u into what happens. So I'm going to write down our x dot equals f xu. I keep writing this down. This is kind of like where everything starts. And say that I have a continuous time system that I can describe as like an equation of motion or something that has a control input u. And let's say this is linear. So if I do x dot equals, and I have x and u now, assuming it's linear, remember this means that I have a matrix without x and u times x plus a matrix, again, no x and u, times u. And this will be A, this will be B. So this is my linear forced, if you want to call it, forced differential equation. So now the question is, okay, this is linear. I should be able to solve it. But now there's like two input variables. So how does this actually, how am I going to solve this if I don't know how u is going to change? And this doesn't quite look like the x dot equals a of x. So what we do here is actually super clever. First we talk about how do we actually control this on the robot. So the way this works on the robot is I have what's called a zero order hold. This is the most common. We'll use this all the time. This is how most, if not all, robots work. So what I have is I have u, and t, t1, t2, t3, t4, tn. So when I control a robot, what I'm doing, if you think about it, is inside my control loop, I get a bunch of sensor readings. I do some math. Maybe I figure out where I am using state estimation. Then I go to my controller. I figure out what I want my control to be, and I spit out a control input u. The u then gets run on the robot for that time step. And then the next control cycle, I do all that same stuff again. So the idea here, kind of the assumption is that I'm going to consider what this control is once for each time step, and then just hold it constant. So, I talk to the controller, I say, what control do you want? It gives me a control. And then the next control cycle, I do the same thing again. But in between those two times, the control is not changing. So what this looks like is, I just hold it constant until the controller gets called again. So the controller gets called at each one of these points. And at that time, the control will change and only at those points. So then maybe I call it again at T2, and now the controller tells me to do this. Call it again at T3, controller says do this. Now it says do this. Now it says do this. The controller is making a new decision at every single time step, and then it's just being constant for the whole time step. And this is called a zero order hold because I'm effectively holding this control value at its zeroth derivative, so at its just constant value. Now this is a zero order hold, or ZOH. Alternatively, what you can see, and which is just as easy for us to work with, but it's just a little less common, is a first order hold. And as you can imagine from the names, I can do this for any order you want to. So first order hold says, give me a value and give me a derivative. And as you can imagine, this is like a little weirder because this is not really how most controllers would work, unless there's some cases where I'm doing torque control where I would do this, but I'm saying give me a value u, and then give me a slope. So how do you want u to change throughout the time step? Say you're not okay with u being constant, you want u to change. I could do this. And then here, have a new value, a new derivative. Here, new value, new derivative. Here, new value, new derivative. Each time, each control call, I'm giving it a value and a derivative, which is a non-zero slope. It can be zero, but I have the ability to specify what that slope is. Where before, I'm just saying the slope, this thing is going to be zero. I'm going to give you what the controller is, all right? Send a torque command of these values to the motors, and then at the next time step, I'll recompute everything. This is more common, but the first order hold is totally just as fine to use as well, and mathematically is just as easy for us to deal with. So now that we've like been specific about how we want the controller to actually implement these things and how we want U to change over time, I can now use that information back into my ODE to figure out what the solution is going to be. So I have our favorite x dot equals AX plus BU. And now let's just think about the time between T and T plus one, maybe right before T plus one. So just I'm thinking about one time step, and my first order hold says that U dot is going to be equal to 0. So throughout this time step, U is not changing, right? So U dot is 0. What I'm talking about here is the time between here and just like infinitesimally right before I change it. So I'm talking about this dt for dt. So you'd agree that this is my ODE for that specific dt given x and u. Now again, I can rewrite this as a new first order ODE of just one variable. So say I want to take a new state variable that is x and u. And now I want to define this thing in state space. I get A, B, 0, 0. So you agree this is equivalent? I just wrote it out in a different, somewhat weirder way. So this is now equivalent to this. And from here, I can do something kind of clever. So now I see this is another first order ODE, but opposed to having just a variable x, I now have x and u. But I can use all the same stuff. So if I were to swap out x and u for z and call this d or something, I'd have the same exact kind of thing. So let's just, as an experiment, say we call this z dot equals d of z. Well, now it's in the form I'm familiar with. So now I can just solve this with the matrix exponential. Now I can just do, z of k plus 1 equals e d dt times z. So what this tells me is that I can solve this equation using the matrix exponential, even if there's multiple different inputs to it. And I can extend this to as many inputs I want to, but in this case, for controls, we think about a state x and a control u. So this tells us I'll be a little quick just to kind of, because we're getting a little tight on time, but what I'm doing is I'm basically saying that I can solve this system. So I can solve this system by doing x k plus 1, and then u k plus 1 equals e a b 0 0 dt, and then xk uk. So what does this thing end up looking like? What this ends up looking like is it has ad bd 0 1. And then the main takeaway we're looking for here is that I can get my discrete time matrices by doing exponential. This is the main takeaway. I can solve linear ODEs using the same matrix exponential. All I had to do was just do this trick where I just kind of stacked it up into a new variable and thought about things in terms of new variable. And then what this gives me is, just to be more specific, is I now have xk plus 1 equals ad xk plus bd uk. So what I just wrote out right here is a method for taking an ODE that is x dot equals ax plus bu. And then I just do this matrix exponential. And what I get is I now get my discrete time a and b. So what I've done is I've taken my linear system and I've discretized it exactly. Because remember, linear ODEs, I can solve exactly with the matrix exponential. I've now solved this thing exactly for AD and BD. And this gives me everything I need for my discretized model. And this is super important. And so what I'll do is I'll add just one extension from a paper I did a few years ago, which is what to do. Basically, what to do when you have affine terms. So I won't go through this, but you feel free to look at this. It basically says, what do I do if my ODE actually has like x dot equals ax plus bu plus d? And it uses just kind of like the same trick I just used, but just keeps extending it like one dimension further. Okay, last thing I will talk about is Taylor series. So a Taylor series, this is like going to be incredibly crucial. We're going to use this over and over and over again. And Zach is going to assume that everybody has used this for a while and is very comfortable with it, which is not always the case. And that's totally fine. So what I'm saying here is that if I'll do first order. So first order Taylor series, this is as simple as it gets. What I'm saying is I'm saying that I want to approximate f of x around some point. So I'll do here. I'll do, say this is my point. So I have the function f, and I want to approximate this thing about this point, x. What I do is I say f of x is approximate, because remember, it's a first order Taylor series, so it's not exact. This is approximate to whatever the value is at that specific spot, plus the Jacobian of f with respect to x evaluated at x. Actually, I'll call it x bar. No, I'll call it xk. I'm okay with xk. And then this thing here is x minus xk. So this, you will see this written over and over and over again. This is a first order Taylor series that's basically saying, take the value right here, take the slope at the current time step, and just assume that's the solution, and then try to predict what f of x is from this. This is a first order Taylor series. I'm approximating the function as linear, and I'm saying what's going on with the function in the region, and I look at the linearized version. As you can see, usually the further and further I go away from where I linearized, my approximation gets worse and worse. But for a lot of functions, I'm really accurate in the neighborhood. It turns out that for a lot of cool control problems, if I linearize about the point I want to get to, and this is something that Zach mentioned, if I linearize at a nice point that's close to where I really want to be, the controller will try and keep it there. And the linearization will stay pretty accurate because I'm always very close to where I started. And for a lot of these control problems, even if they're very crazy and nonlinear, so for instance, like the inverted pendulum where it does like the cart pull and it spins up the pendulum and has to like balance it up there, that's a very nonlinear problem. The differential equation that describes how that moves is nonlinear. But if I linearize it about, the control point I care about, which is having this thing stand up and down, once I do that, the controller works super well because I'm never actually leaving that far from where I linearized about. And then the last thing I'll leave you with is if I have a change of variables, so say that I want to talk about things in terms of deltas. So say I want to say that x is just xk plus some delta x. And don't get hung up on this. I made this up, right? I just pulled this out of the sky. I said, here's a dx. Let's just use dx to internally what we'll call the difference between x and this xk that we're linearizing about. And oftentimes you'll see this as x bar, and I'm going to write it as x bar. I think that's a little easier. Bar, 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 x bar. So I linearize about x bar. Lin about x bar. And now I just kind of made up this delta x business. I said, here's delta x. And now let's rewrite this exact thing right here. So here's the first form in which you'll see it. This is like exactly what's on the quiz. So the first form you'll see it is this. The second form you'll see it is I just substitute in our new like variable definition inside of here. What this tells me is that I substitute x bar plus delta x. Delta x is approximately f of x bar plus df dx at x bar. So this is the same Jacobian times dx. These are the two forms of Taylor series. And again, we're just talking about one input here. Next week, we'll go into much more detail and we'll talk about two inputs and control problems and how we linearize those and specifically why we're doing that. I think there's like a cool intuition there. If we had the function, like, why are we trying to approximate anything? And there's like some kind of interesting reasons as to why we always do it. But needless to say, here are the two things we really care about. These will be on the quiz, and this is just the two ways we can write down a Taylor series for a function f. And the only difference is that between them, I've just introduced a new delta x variable that just makes our lives a little easier because this is kind of a weird term to carry around. And a lot of times we care about these deltas and it's a little easier to express what we want to do in terms of deltas. And this is also the way that Zach will always do it in the second way, but this is the way that you learned in high school. All right, so I think that's all we're going to get to today. Next week, we'll go through, I guess, like more linearization stuff, the derivative formalisms that I didn't get to today, and then how we linearize for systems that have controls and inputs, because those are the ones that ultimately we care about the most in this class. And then do some homework one stuff. All right, so happy to answer any and all questions. I'll turn the recording off.